In this video, we'll be talking about a different way to allow for concurrency, to allow for controlling how you interweave transactions together such that they still achieve serializability in a way that doesn't actually involve using locks. So right now, we've been using locks to basically do everything. What do locks do? Locks make sure that you only ever perform actions that could not in any way allow for non-serializable behavior. That you make sure, okay, if you're going to read, you get a shared lock. If you're going to write, you get an exclusive lock. And those locks stop other transactions from doing things that might cause problems. And why are we using locks to do that kind of complicated lock, unlock, passing, two-phase, commits, and all of that? It's because we want serializability. And why do we want serializability? So that each transaction is atomic. Each transaction looks like it began and ended at the same time, that it achieved all of its things without other transactions getting in the middle of it and changing the data out while this transaction is running. And the way that locks do that is by making sure that the only actions you or other transactions are allowed to do are ones that won't affect each other. And so what another term for this way of controlling concurrency is called, it's pessimistic. It basically says we're going to assume transactions will do bad things to each other. We're going to assume that transactions will change data in ways that would generate non-serializable behavior unless we stop them, unless we make sure that we don't allow that possibility. However, locks aren't the only way to ensure you get serializable schedules. And we're going to talk about those other ways this week. Alright, so the basic idea for this is we optimize for the case where conflict is rare, where most of the times, even if transactions are reading from and writing to the same data, most of the times conflicts actually don't happen. And so the way that we accomplish this is by breaking up transactions into three phases now. So what we do is we have the read phase, where transactions are able to read from the database, and if they ever make any writes, they do that to like their own private copy of the database. And then what they can do is they do what's called validation, where they say, okay, here are the places where I want to write to the database. Make sure that you don't have any conflicts where you would do these writes to the real database, because it's like so far you've been doing all your writes to your little private world. And then if validation passes, then you can write your local changes out to the main database so that other transactions can read them. Now, of course, if your validation step fails, like the writes that you made to your private database, if they were exported would cause conflicts with other transactions, then you abort, then you roll back. And so why is this a good idea? Well, I guess the problem and the good thing is that actually most transactions on the database are reads. So it means that most of the time you're doing select statements, not insert statements, not changes to the tables, not update, not delete. Most of them are actually reads where you're trying to, do those joins and figure out what data is here and find if any data has changed, things like that. And readers never conflict with each other. And the other thing is, even if you have transactions which do writes, which do change to the database, most of the time those transactions only change or only read from a small part of the entire database. You're only adding a couple rows to one table, or you're only changing a particular column in a table, things like that, so that even though you are writing changes to the database, many other transactions won't even care because they won't be looking at that part of the database. And so the whole overhead of getting all of those locks and releasing those locks and checking for deadlock and all of that overhead, you don't have to do if really these transactions would never have touched each other to begin with. And so you're going through all of that process of getting and releasing locks when you don't need to. So I'm going to go over a little bit more detail on what's called validation. This is an alternative to locks. And so the goal here is to once again guarantee that non-serializable schedules cannot pass. And so the way that the validation method achieves this is you, in a process, find an equivalent serializable schedule to the schedule that the transactions want to do on their own. So you basically, just like when we talked about conflict serializable schedules for locks, we're doing basically the same sort of thing here. We're trying to make sure that the given schedule we have can be serializable. And so the way that you do this is every time a transaction starts, you give it a timestamp so that we can see which transaction started first and proceed from there. And then what you do is you make sure that the serializable schedule that you can generate is the same as if transaction 1 started and finished, then transaction 2 started and finished, and transaction 3 started and finished, so that the order of the transactions in which they start would be the same as if you had just done the entire transaction right at the point where it started. So let's assume that we have two transactions, transaction I and transaction J, which both have time steps. Transaction I's time step is smaller than transaction J, meaning transaction I is the older of the two transactions. And we can be sure that these two transactions are serializable, meaning that transaction I appears like it did all of its actions before transaction J even started, if one of these three conditions hold. The first one is that transaction I completes its write phase before transaction J starts its read phase. And we'll talk about these conditions in more detail in the next couple of slides. So if they don't make sense as I'm reading them right now, I'll explain them in more detail. The other option is transaction I doesn't write to any objects. So it's a reader in the sense of whether or not there's any conflicts between these schedules. And transaction I completes its write phase before transaction J starts its write phase. Or, the most complicated one, transaction I doesn't write to any object that transaction J reads from. Transaction I doesn't write to the same element that transaction J writes to, and transaction I completes its read phase before transaction J completes its read phase. That's really messy. We'll get through those in a bit more detail. So let's break those down again. So once again, for these two transactions, we're assuming transaction I occurs before transaction J. And so the easiest one to talk about is if transaction I completes its write phase before transaction J even starts its read phase, this is just by definition serial execution, right? Transaction I did all of its reads and it finished its validation and it finished doing all of its writes before transaction J even started its read phase. So transaction J has no way of seeing any of the old dirty data. It only gets the nice clean data that transaction I changed before it. So that's serial execution. Transaction I basically did everything before transaction J even started. Okay, that's the easy one. The slightly more complicated one is transaction I doesn't write to any object that transaction J reads from, and transaction I completes its write phase before transaction J starts its write phase. So what does that mean? It means transaction I may read from a whole bunch of different things, but the places where transaction I writes to are different from the places where transaction J reads from. So even if transaction J is still in its read phase, because transaction I doesn't change any data that transaction J wants to read from, it'll be fine. And so that means that we won't get these write-read conflicts. Transaction I is never writing to places where transaction J wants to read from, so transaction I is able to have more time to get done with its job while transaction J is starting. So once again, this means that we don't get write-read conflicts because transaction I never writes to the same places that transaction J needs to read from. So you're allowed to allow transaction I to have more time while transaction J is running. And this last one is the really messy one. Okay, so it starts with transaction I doesn't write to any object that transaction J reads from, just like the previous one. And transaction I doesn't write to the same element that transaction J writes to. So it means not only does transaction I not doesn't change things that J wants to read, transaction I also doesn't write things that transaction J wants to write to as well. And this means that if both of these elements come true, this means that transaction I can complete its read phase before transaction J can complete its read phase, because now we have even the most stringent criteria here that says, okay, transaction I will not read any data or doesn't write any data that J needs to read to, so that we don't get the conflicts from write-read. And transaction I doesn't write to the same things that transaction J gets to, so you don't get the write-write conflicts. And as long as transaction I completes its read phase, like it finishes reading all its data before transaction J finishes its read phase, this means that we're sure that the things that transaction J writes to, transaction I can't read from. And so, once again, another way of saying this is you're allowed to interweave the things from transaction I and the writes from transaction I and the reads from transaction J, or the writes from both of them. Those are all fine to interweave, but as long as we always make sure that we make sure that transaction I gets its reads in before transaction J gets its write in. So you never get these write-read ordering. And once again, this is a really kind of complicated rule scheme to basically ensure that when you're working through these transactions, that you always get the transactions conflict resolved in one direction. This means that you always make sure that the transaction that started first gets access to the data first and gets to do its writes first before the other transaction tries to read in those changes. And so really the whole process is just to make sure that every time you have a conflict between two actions in a schedule, it favors the one that should have happened first, the transaction that started first, gets to be the one that beats the other one in those conflicts. It's always, if you started first in the conflict, your action occurs first as well.